I shall talk about some recent work of mine in trying to understand some perturbative type 2 amplitudes for BPS interactions. So I shall begin with a brief introduction and motivation to this audience. Of course, none of this is needed, but essentially this will help me set up the problem. Then first I shall talk about the string amplitudes in 10 dimensions, which is the well-known case. I'll assume that is for the interactions I'm talking about. Then I shall talk about the interactions in 9 dimensions, the simplest case. Then I shall generalize to 8 dimensions, which is significantly more complicated. Then I shall talk about the structure of the amplitudes in general dimensions. So first, the introduction and motivation. The main idea is to try to understand the effective action of string theory. Not necessarily right now we're trying to understand phenomenology, but at least we look at simplest toy models where you can solve the theory exactly, at least for a certain class of interactions. The main aim is to understand the duality symmetries of string theory, namely various perturbative duality symmetries like T-duality and also non-perturbative U-duality symmetries. But at the end of the day, it's good to have a good handle on these duality symmetries because they are useful in defining the theory anyway beyond the perturbative regime. And however, this has proved to be difficult to obtain in general circumstances beyond flat space with Riemann fluxes turned on in cosmological singularities, time-dependent backgrounds. This has proved to be generally difficult for various technical reasons. Now, this effective action, this encodes the S matrices of the theory. We are looking at on-shell scattering amplitudes in the way string theory is described. I'm not talking about string field theory, but standard string perturbation theory where the various operators are on shell. And they contain non-trivial moduli dependence on the interactions for various compactifications. So when you compactify on various internal manifolds, there are various scalar fields which show up, and the couplings of these various interactions are moduli dependent. So generally it's a hard problem to try to figure out what the moduli dependence is. Because that is essentially the answer to the question, most general question. This has not been possible in general, though certain terms in the effective action can be calculated in special cases. Of course, whenever this happens, this has to be a consequence of strong symmetry arguments. For example, supersymmetry and special geometry. So physical string theories and certain topological string theories have made possible these calculations. And for the cases I'll be talking at, the symmetry is supersymmetry. We shall focus on certain BPS interactions in toroidal compactifications of type 2 string theory, which preserve 32 supersymmetries. These are simplest string compactifications you can get because it preserves all the supersymmetries, so the calculations are easiest in some sense. That is for a certain class of interactions that we're looking at. These are the 4 graviton interactions of this kind. R to the 4 is a schematic here. I'm not going to give you the details of the space-time structure here, but at the linearized level, it involves the 4 graviton scattering amplitude in string theory. And then there are all momentum dependence comes out. For example, the next term in interaction is d to the 4 r to the 4. D to the 4 actually in the momentum space really means a square plus t square plus u square in Mandelson variables. The next is d to the 6 r to the 4, which is s cubed plus t cubed plus e cubed. So you have this r to the 4 interaction, and then you have a perturbative expansion around this guy in power alpha prime. So there's no d square r to the 4 simply because s plus t plus u is 0, and we are looking at on-shell processes in string theory. We are looking at 4 graviton interactions. One can generalize this to other interactions, but these are the simplest ones, the 2 to 2 scattering of gravitons. And this will be the viewpoint I'm going to look at today. So these interactions are half BPS, quarter BPS, and 1/8 BPS interactions. If we go to the next one, this is d to the 8 r to the 4. This is the first non-BPS interactions. And these are much more complicated. I shall not talk about non-BPS interactions at all. Just only BPS interactions. Now, after you compactify, these coefficients are modular dependent. And the modular dependence of these coefficient functions can be calculated using various methods, using both space-time and world-shaped techniques, supersymmetry and duality. Essentially, because of the very large amount of supersymmetry, you have big U-duality groups, right from SL to Z in 10 dimensions all the way to A88 in 3 dimensions. So that somehow helps you. This U-duality group is intimately connected to supersymmetry because once you start doing supersymmetry, the duality groups are not well constrained. And here, this helps you in solving, at least for these BPS interactions, various conjectures have been made. Of course, how much you can calculate from first principle is a different issue.
So these are all like exactly known?
Exactly known, yeah. Most of them are conjectured, particularly the non-perturbative parts, calculations in D-instance backgrounds. You kind of try to duality covariantize them and get the answer, but you don't know how to calculate from first principle. That's how you have to do. So these U-duality coefficient functions can be expanded around weak coupling in the string frame. That is what is going to be the main interest of my talk today. And let me look at the perturbative contributions. The perturbative contributions take this form. This is the standard T-duality invariant dilaton. So T is going to be the dimension of the internal torus. So I'm going to look at compactifications on TT, small d. Okay? So non-compact dimensions are 10 minus d. So this is the T-duality invariant dilaton in d dimensions on TD. And this is the only other modular dependence, the perturbative modular dependence. This depends on the metric moduli and the moduli coming from the NSNS2 form. Okay, all of the one-to-one moduli dependence comes in the non-perturbative parts. So this, for example, the G equals 0, this is genus 0, tree level and so on. So the main question is, this is of course universally fixed. What is this? Can we fix them for this kind of complex? And generically we would expect this G to go from 0 to infinity for a generic set of interactions. But these BPS interactions are special. For the R to the 4, D to the 4, R to the 4, and D to the 6 R to the 4 interactions, n is finite. So R to the 4 receives contributions only at genus 0 and genus 1. D to the 4 R to the 4 receives contributions at genus 0, 1 and 2. And D to the 6 R to the 4 receives contributions at genus 0, 1, 2 and 3. And it stops beyond that.
What is it?
N is the number of loops, in the string loops.
Is there a unique R to the 4 structure consistent with the supersymmetry?
Yes, it involves only the wild types.
So this is unique R to the 4 structure, unique yes. to the 4 R to the 4 structure, unique.
Exactly. The space-time dependence is uniquely fixed just using string theory, string scattering amplitudes.
Strings not using supersymmetry. Supersymmetry does not uniquely fix these.
The space-time structure, you just do a tree-level scattering amplitude, get the space-time structure. Then you build up the whole supersymmetry multiplied.
I see the space-time structure for 4 graviton amplitudes is uniquely fixed using, you say, string scan.
Yes. I see. And then you try to supersymmetry as a whole multiple.
But suppose I ask the question, what is the most general, whatever derivative term that is consistent with supersymmetry?
Yeah.
Does that fix it to be of these forms?
I don't think so, no. Yeah, there could be various contractions which would come up. Supersymmetry won't fix.
Which supersymmetry will not?
Yeah. And then the problem is, with so much with the problem is you don't have an optional superspace. So the linearized level, a lot of things work. Then there's a linearized superspace due to Howell Quest from many decades ago. But that is going to try to see some of this structure comes out, but it's not, you don't really fix it uniquely, even beyond. I mean, even a lot of this, for example, if you look at say f5 to the 8, there's a term like this 8 derivatives. I mean, this supersymmetry doesn't tell you because it doesn't exist in linearized superspace. For that, one is to actually do a string amplitude, which no one has ever done, but in principle that can be done. So, in my conventions, phi is a 10-dimensional dilaton. Vd is the volume of TD in the string frame, not because I'll be often moving from the string frame to the Einstein frame. This is the volume of the string frame, and I defined already by G and Br. So, of course, Fg, Gij, Bij is T-duality invariant. So, there's a whole modular form, which is the coefficient of this interaction is U-duality invariant. When you make a weak coupling expansion, term by term in string perturbation theory, the coefficients are T-duality invariant. And this is what's called a modular form of ODDZ. This is the T-duality, a discrete group which is broken due to string invariance. So the main question is, can we fix this? That's for this class of introduction. So how do we actually calculate Fg? So Fg is given by the integral of the moduli space of Riemann surfaces of the integrand is often complicated. Hence they are not easy to calculate by performing the integral directly. So most of it is going to be completely integral of a supermoduli space, which may be split on what you know, in principle is difficult to do it. But at least in this case, if you are lucky, it becomes a moduli space. So okay, first you have to integrate over the positions of the vertex operators, you get a complicated mess which depends on the world-shape moduli. Then you have to integrate over the moduli space. And the integrand is quite nasty. So most of the times you can't do an integrand because even in the field theory limits, these are quite difficult to calculate. So that becomes hard. So what I shall try to do is never calculate this integral derive. But at least for this class of interactions, I shall found out a differential equation satisfied by Fg. And then solve it by using appropriate boundary conditions. The appropriate boundary conditions are known decompactification limits and some unitarity norms. And these equations will turn out to be Poisson equations with very specific structure of source terms. And in line and 8 dimensions and solve them exactly. In lower dimensions, I'll just write down the equation. So that is the goal. So we now analyze this string amplitude starting from the simplest case of circle to compactification. So that flat space 10 dimensional case is the simplest case, and then start with circle compactification and go on to lower dimensions. And I shall make use of one fact, which is the result to Berkowitz, that the perturbative 4 graviton amplitudes up to genus 3 are same in type 2 and type 2. It's not a statement of t-duality, but it's an independent statement. They have to be same.
Yeah, this is true only for torus compactifications?
With maximal supersymmetry. So only for the BPS ones. Up to D2 6. It doesn't hold for D2 8 and essentially because there is this, when you do the calculations, the T8 and epsilon 8 in the light cone gauge. So there's a right and left movers. Only the T8, T8 and epsilon 8 solve them to be solid. And they actually turn out to be the same answer. But it doesn't hold beyond genus 3. And that's good enough for us because these are BPS and we are looking at anyway amplitudes up to genus 3. So this is the how we can do the calculation. So first I'll tell you how to do this in 9 dimensions. This I'll spend the maximum time on this because the simplest case to give you the idea. The rest of our complicated generalizations. Now so we'll see how this works. This is a warm-up example. So this perturbative equality implies the invariance and the interchange of okay, so R is the radius of the circle in the string frame. So perturbative equality implies invariance and the interchange of R and 1 by R, keeping the 9-dimensional T-duality invariant dilaton fixed. So at tree level, it's straightforward the answer is. You take the 10-dimensional answer, multiply them by a factor of R. That is all there is in tree. This is trivial. If you do it in 10-dimensional action, the answer you don't have to do anything extra. Just multiply by R. And the dilaton dependence automatically is the way it should be. So this is the R to the 4 is a zeta 3, D4 R4 is a zeta 5, and D6 R4 is a zeta 3 square.
Winding both principal contributes because they produced in pairs.
Yeah. So it's a flat 10 dimension. And then it's emitting the circle.
And these coefficients are determined by scattering amplitude.
Scattering amplitude. For example, so let me maybe I'll write down the general expression to be clear how they come out. So what happens is that tree level is you get a e to the minus 2 pi here, and you have r to the 4 here. At tree level, what you will get is a linearized approximation because you're looking at string amplitude, linear particular pressure, and what you get is minus something like this. Numerical factor, this is what you get. And now you're going to explain. This is what you get.
So this is just the resolution of the amplitude for gravity.
So just one example. So the first term actually has a 1 by STU.
Yes.
This is the supergravity. Then the next contribution is zeta 3.
And by R to the power 4, here you mean that the polarization tensor contracted in an X-ray.
Exactly. So linearized level, you will have 4 polarization tensors and 8 puzzle moduli. In a string partition of the calculation, but then you just see that this comes out from a certain fold contraction and the full moduli. So these are the first 2. These are the first 3 terms in expansion. So at tree level, you know what we are talking about. So now let's look at genus 1. So this is the expression for the R to the 4 amplitude. It is reasonably tractable. There is this integral. And I'll define what this is.
Sorry to be so ignorant. How do you get those zetas?
Yes, let me just write down the formula here. So what happens is, you use this formula, log of gamma 1 minus z. Is actually the Euler maximum constant plus over zeta
Nice. From the data expansion.
Then you expand. And you see, and it's only odd cause of theta rather than plus and minus sign.
Nice.
So only the foreground amplitude odd cause of theta. And in fact, the remarkable thing is now you think about it from today's point of view, there are no what about these multiple zeta values which come up. These are all ordinary Riemann zeta functions. But when you look at high graviton amplitudes,
low transcendentality.
Low transcendentality. But because there is an important question in mathematics, I mean, how many, for example, when you go to higher orders of higher transcendentality, are the Riemann zeta function the only basis choice here? And for example, I mean, at certain orders, for example, in the when transcendentality is equal to 11, it turns out that you don't have ordinary zeta, Riemann zeta functions coming out at very high order projection for the 5 and 6 graviton. So this is the genus one. I shall define this in a moment. But let me give you the expressions. This is the R to the 4. So it's an integral of a moduli space here, the fundamental domain. The lattice factor which I shall explain, and I shall also explain what this is. And I have just brought out these irrelevant factors here. This is called the Hackling convention. So the difficult part I'm calling for. I brought out these trivial parts here. And this is the d to the 6 R to the 4. So this part just involves this pi cube, zeta 3 comes out. So this is just proportional to the R to the 4 part. And there's this new novel part. So this becomes a bit of work because I've already integrated the 4 vertex operators over the toroidal world sheet. It's after that. Now here basically this modular dependence doesn't look too complicated. So this is a warm-up example, but it gets more and more complicated as you go higher and higher genus.
You said this, but what was omega, please?
I'll explain it. So okay, so here's the definition. So F1 is the fundamental domain of SL2Z, that's the keyhole. D2 omega is the volume here. 2 d omega 1 d omega. This I have an extra factor of 2 compared to any place in the literature. You want to follow the details. So I've explained this part. I have to tell you the lattice and what this E's are. The E's are SL2Z invariant non-monomorphic Eisenstein series given by this lattice sum. So the origin in lattice space is removed because there's a singularity and is an infinite lattice. And this is actually SL2Z invariant. So you said omega to A, omega plus B by C, omega plus D by AD minus BC is 1, ABC at integers. This is actually SL2Z invariant. And one can perform a large omega 2 expansion. I'll give you the answer. I mean, what you need to remember, there are 2 power behaved terms, and the rest are exponentially suppressed. And this is some theoretic fact which can. And finally, I must tell you one more important fact, that this ESS satisfies a Laplace equation. This is the SL2Z invariant Laplace. They satisfy the Laplace equation. And finally, I must tell you what the lattice factor is. This is the lattice factor. R square is equal to omega square 1 15 rows momentum. This is the lattice. So now I've told you what is the exact integrand for this one loop BPS interactions. Now it's a quite difficult task to actually solve it, because to do this integral over all of moduli space, and even knowing this exact expressions doesn't help us. This can be done, but it's quite complicated. And one has a method of orbits, so break it into various orbits of SL2Z, and you have to break Eisenstein series into alternative representations of SL2Z and then do it. It's not very simple, but it can be done. So what I shall do is, I shall try to do it differently. The point is, when you act with this SL2Z Laplacian on the lattice factor, it's equivalent to this action where lambda is R square. So what that will be to never directly calculate the integrand, but act on the integrand with this guy.
What is R again?
Yeah, R is the radius of the circle. So the only R dependence is in Z lattice, in the exact integral. So you act on the integral. So you act on the entire integral with this guy. It acts only on Z lattice, and you replace this with the Laplacian of the world sheet acting on the lattice. Then you integrate by parts. Right. And when you integrate by parts, the remaining integral is either 1 or Eisenstein series, which are again eigenvalue, which satisfy eigenvalue equations. And you have to just be careful about boundary terms.
Which is, you're saying the thing that appears on the integral is the right hand side.
Exactly.
Now you got exactly that combination on the right hand side?
No. See, what I'm going to do is the following. Let me look at any one of the examples. Say this one. Say this one. Sorry. Say this one. All I'm going to do is act on this with this lambda square del 2 del lambda 2 plus 2 lambda del 2 del lambda.
So you have differential.
So it acts on this only. I integrate by parts. This satisfies the eigenvalue equation. And what I'm going to do is only boundary terms. And that's good news, because the boundary asymptotic nature of these integrands are often much easier to calculate. In fact, when I come to units to amplitudes, I mean, these are not things very well understood to mathematicians, so this is very useful for us. And this is only for even for BPS interactions. So let's see how we can proceed.
So just one. So how is R hidden inside that?
The only R dependence is here. Let me give you the answer here.
I see.
The only R dependence is here.
Okay, I see.
The momentum and bindings. Sorry, you said I was mixing out. Omega was what again? Please?
Omega is the complex structure of the torus. I've integrated the fundamental domain here.
Yes.
This is the general study in all dimensions that is coming for all BPS interactions, but this is the simplest.
So you will finally get a differential equation in the variable R.
Exactly. In the t-duality variables, and then hopefully that will be easier to solve in direct with the integrals, which I shall show you for the case of the
Yes.
So that's the whole thing. So that's the whole point of this project. I mean, at least for this BPS interaction, where things are tractable, try to do it in detail. So the 9-dimensional case is the warm-up example. So let's proceed. For the R to the 4 interaction, you do this thing here, and the integral was just 1, so this becomes a total derivative. And it just vanishes, and you just solve it. And you just solve it, this is what you get. Remember, lambda is R square. These are solutions of lambda to the power alpha. It's a Poisson equation. So solution is lambda to the power alpha, solve for alpha. And you impose the perturbative equality of type 2 and type 2 with simplicity. This is what you do.
Oh, you got 0 on the right hand side. I thought you had something from the boundary term.
Yeah, that will be, I'll come to that. So this was, for R to the 4, this was 1 times the Laplace. That's the boundary term. But But this I shall spend a lot of time on telling you where the boundary terms belongs in. That's the difficult part. And I'm just telling you the answer here. And here you see, I use this perturbative equality to have this r plus 1 by equality. And this overall coefficient is just fixed in the 10 dimensional. So this is so far so good for the R4. Now so let's look at it for the R, for the G to the 4 up to the 4. This is what we got earlier.
You had a second order differential equation, you had two.
Yes. Right. So those then and overall right. So then I use the perturbative equality. That fixes one, and another overall normalization is fixed using the 10-dimensional decompactification. Because the term linear in R survives in 10 dimensions.
Lambda itself was
R square.
R square.
Right. So this is solved by lambda to the alpha, or alpha is some. So the two values, and I just impose perturbative equality.
What do you mean perturbative equality, sir?
This is symmetry and the argument to 1 by.
That's right. Yes. Thank you. So the T-duality fixes one combination.
The point is very compactified. In taking either 2A or 2B, as if you write an equation. RA is equal to 1 by RB. The radius of the circle in the 2A theory in the string field, the radius of the circle in the 2B theory in the string field. And the other equality is RA is equal to E minus phi B RB. So here you can check actually e to the minus 2 phi R is the same. So we make this transformation. And R1 to 1 by R is this perturbative equivalent.
Yeah.
So when you send 2 into 2, it's exactly the same answer. So this is R to the 4. Let me now go to D to the 4 up to the 4. You have this combination here, you use minus 2 here because there was e to the second resistance series, which gives you a plus with eigenvalue minus 2, with eigenvalue 2 here, bring it to the left hand side, throw away boundary term. So boundary term I mean let me write to show me away. I'll look at it later. So this is this solution. The overall normalization again fixed using supergravity because this diverges as R goes to infinity. But these are needed for unitary construct because like infinite number of things add up to longer terms in effective action. And so again, it's easy to see here what the answer is. So this is the point. This is somewhat simpler to the analysis in this way. Even for the 9-dimensional case, where I think we're not very simple. And finally, for the D to the 6 after the 4th term, there was a third Eisenstein series, which is eigenvalue 6 here. So this is what you do. This term is trivial. There was one part which was proportional to the after the 4th term moduli of a factor of zeta 3. This term is trivial. This is the non-trivial term. And again, you fix the coefficient using supergravity. So for the 9-dimensional example, I've shown you how to fix this coefficients exactly.
I see. So you keep expanding the theoretical structure to one higher order every time, and that is why you get products of zetas.
This is one loop. This is one loop. This is not true.
How will be the product of zetas?
Oh, the product of zetas. Okay. So this one, right? This one.
Sorry, this is one loop.
This is one loop.
Yeah, so I don't know how you get the.
Yeah, one loop. The expression is quite different actually. One loop actually wants to do the integral. The one loop expression actually has this d to omega by omega to square of the fundamental domain. To start with, this is a complete expression to start with. The product over these four vertex functions. Okay, each of them is integrated over the toroidal worldsheet. Then you have this, this log I, log I1 to the alpha prime S, log I1 3 to the alpha prime T, and log I4 to the alpha prime 2. So this is 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 2. But log I is really the scalar property. So you have to do this integral concept. So this is really this log of mod theta square plus tau square and exact. So this is much more complicated.
Anirban, I should have asked you this at the beginning, but you have this equation which is del omega squared was equal to some derivatives in lambda. Where did that equation come from?
That I deduced. You can just prove its identity.
And you can prove it using the explicit form of the integral?
No, just take the lattice factor. Right? Just prove it.
I see.
Exactly. Just get systematic.
I can't think of this as a consequence of supersymmetry.
No, the lattice factor arises all over the place, even in Poisson extreme. Yeah. The only point that the integrands won't be so nice. So it won't be particularly useful. So then, yes. Okay. So we have blocked total derivatives. I'll come back to that in great detail because those will be the infrared divergence and string theory. And those are actually dimension dependent. They don't exist in all dimensions. So now let's go on to genus 2, which gets like more complicated. And for r to the 4 is 0. Okay, because r to the 4 stops at genus 1. Then you have d to the 4, r to the 4. d to the 4, r to the 4 is still more or less practical. I'll review what these things are. But this is the radius, this is the measure of this genus 2 moduli space. There is a genus 2 lattice function. Right? And again, put the simple stuff outside. This is the I2 hat. And I shall define this for you. And this is the d to the 6, r to the 4. I shall also define what this object phi is. Because now you say no more something very simple. I'll tell you what phi is. So here, let me go through the definitions. F2 is the fundamental domain of SP4. So one can write it down. I'm not writing it out because we don't need it that way. I'll just tell you whatever it is going to be. But it's known to mathematicians. And there was this measure here, d mu2. Let me tell you what that is. It's a little bit crucial. This measure is defined this following. You take the period matrix, the 2 by 2 period matrix on the genus 2 Riemann surface, and write it as x plus I, where when x and I, y are really 2 by 2 matrix. It's a symmetric matrix. And this is a determinant of y2. And then you have this waste product. So for example, for the one loop Riemann surface, this would be really d omega bar. This would be omega 2 because it's a 1 by 1 matrix. It's a okay. So this is the definition of the measure.
This is what is called as the Peterson
measure. For genus, actually genus H, this is the determinant y to H plus 1. And this I0 from 1 to 2. And this is the lattice factor. This is a little more complicated because it involves the period matrices. And y is defined this way. The y inverse eigen entry is y inverse eigen. So for example, you see at genus 1, this would be just 1 by omega 2. Right? And this would just be this m plus n omega mod. And finally, this phi omega bar, which arises in the d to the 6 r to the 4 interaction, is what's called in the mathematicians the Kawazumi-Zhang invariant. It's an SP4Z invariant on the fundamental domain of SP4 set, and this is quite complicated. So it's not known exactly in a very compact form. But again, I shall show you just need to know the asymptotes because everything is local as a boundary.
Because this is the genus 2 counterpart of the Eisenstein.
Exactly. So now I'm going to repeatedly use this relation in terms of to take the lattice sum here. This is what you.
And that phi thing you get by direct evaluation, by direct computation.
Exactly. I mean, exactly. So what people did was they got something here and they showed that, I'll tell you, it also stands for some Laplace equation. And then what they checked, it was known in mathematicians, by mathematicians like Zhang, Kawazumi, and Fortins and others, that this is what's called Zhang-Kawazumi. I mean, this was known only a few years ago in mathematicians. And this actually vanishes for genus 1. So it only exists for genus 2 and beyond. For genus 3, this has nothing to do with string theory. So only genus 2 it shows up in string theory.
And the calculations that people do in string theory, this is an RNS formulation?
You take this, basically you take this Rohford form answer. Do the integrals. And then you are left with something. And that something turns out to be the answer. Because this is a 4 point is NSNS sector, so this one is also. The other one, it's a simple problem. So again, this is the trick. So let me now tell you what we get. For d to the 4, r to the 4 interaction, we get, there's a boundary term. I shall tell you some detail going through it today. Leading to this. This again, the 10-dimensional answer you managed to get the overall normalization. This is the present answer. This is exactly matches with the literature. And we have got a boundary term right here. This one, fundamental domain of there's this integration by parts here. So let me tell you a little bit about how we could neglect it because it will come up later. So to see why it is neglected, we parameterize the period matrix in terms of this. And then the boundary of the moduli space has two components. And of course the third component is the trivial intersection of these two. These are two divisors. One is a separating node when the genus 2 Riemann surface splits into two tori with two additional punctures. So this is this origination. It separates this way, and at the end, select with the two tores here with a puncture. This is the separating node. And the other is a non-separating node where the Riemann surface degenerates to two dots with two additional punctures. It is this node here. So this one stays as it is. This one also stays as it is, but this one becomes infinitely thin, pinches of you. Okay. So this node is called the non-separating node here, and you are left with just one Riemann surface with two punctures. So this one is really cool. So these are the boundaries of moduli space. I have to look at the contributions, what comes from here. And
contributions meaning the extra R dependence. That's what.
no, I just want to show you why this vanishes.
The issue arises because you have a differential equation in terms
Right,
of R,
right.
and then you want to know whether there are extra R dependencies which.
Well, no, I mean I acted on with this. On the right hand side, I just got rid of this.
To get the differential.
Right. So the question is, why should I throw it? I mean, more than half of my talk will be spent on what cases we can't throw it on. Let me start here.
He got the differential equation by asking something was zero by an integration of x. And is that back?
Yes.
So in terms of the period matrix, this is the period matrix. I'll tell you what the degeneration nodes correspond to. So the separating node is obtained by taking tau to 0, which is the off-diagonal part. So then it separates here, the separating node here, while keeping tau 1, tau 2 fixed. So then tau 1 and tau 2 become the complex structure modulus of these two 1. And the non-separating node is obtained by taking tau 2, this guy here, to I infinity, while keeping tau 1 and tau fixed. So for a d to the 4 up to the 4th term, the boundary term from the non-separating node, which is tau 2 into I infinity, trivially vanishes from the lattice because of the exponential separation. And from the separating node, one has to do a contour integral in the tau space around tau equal to 0. There is the pole, because the integral was just 1, so it trivially vanishes. So there are the contributions. Great. So now let's go to the d to the 6 out of the 4 interaction where we can't throw away such terms. So in d to the 6 out of the 4 interaction, you have this expression here. And now we need to integrate by parts. We integrate by parts by using the expression for the Laplacian on this, which I am not going to give you a bit of a mess, but it can be done. And when you integrate by parts, you will of course get boundary terms plus a term with the Laplacian action is Gaussian invariant. The important thing is to give this equation where we have used the fact that the Gaussian invariant satisfies the Eigenvalue equation. So this is the equation we get. And these are the boundary terms which are there. Let me tell you what is boundary terms. The boundary terms are this. This doesn't look like a boundary term because d mu 2 actually is a 1 by determinant y cube. So d mu 2 determinant y cube is really integral d omega 1 1 d omega 1 1 bar, d omega 2 to d omega 2 2 bar, and d omega 1 to d omega 1 2 bar. So this is really a boundary. And where idea is defined in this way. This is completely a boundary term. So the good news is we have to know much less about the Gaussian invariant on integral. In other words, we need to know the properties of Gaussian invariant and the lattice factors and the imaginary part of the period matrix. Only nearly separating and non-separating. So that's an easier one. So let me tell you what the expressions are for these various asymptotic measures. First, determinant y behaves this way in the separating node. It behaves in the same way in the nodes. Only the subleading corrections have different power because it's a factor. This is known. The Gaussian invariant at the separating node. This is when tau going to 0. It has this dependency. And the crucial thing, this is a log tau. That's the only thing you want to remember from this slide. It's a log tau. And the non-separating node is a form of complicated behavior. It's a power series expansion. There's a t, order t, there's an order 1, there's an order 1 by t, and exponential is a plus t. But t is this complicated combination. And I have to tell you also what phi naught hat and phi 1 are, because I should be meeting them later. So phi naught is this complicated expression. It's essentially involves roughly like the log of the propermeter, the scalar propermeter on the torus. That is phi naught here, phi naught hat here. I have to tell you what phi 1 is. Phi 1 is given by this. This is the Eisenstein series. This is something more complicated. This will tell you what D22 is. D22 is a special case of what's called a Kronecker Eisenstein series. This is given by this expression. It has these phases compared to the original Eisenstein series. But anyway, these are tractable expressions. Not particularly complicated because we need the bounds. So that's the expansion of the non-separating node as an imaginary tau 2, then order 1, 1 by imaginary tau 2, 1 by imaginary tau 2 square to infinity. But now this phi naught, I have absorbed this term here, this is the expression. And the Z2 lattice factor gives them trivial. The separating node is just separated into two lattice factors, corresponding to toroidally complex structure tau 1 and tau 2. And the non-separating node is that. Non-separating node is just sent imaginary tau into period. So we know all the degeneration limits of these various form elements. And generally we need to evaluate expressions of the form. Because remember, we needed to do integrals like this. Like this here. So there's a del bar here and some A, something general B here. These kind of integrals we need to do. I should of course keep all the details, but with answer. We need to do integrals of this kind. where when you localize, say,
in this, you should be able to give physical interpretation to all these boundary points.
Yeah,
you can do that.
Yeah, so essentially it's this propagation of massless modes. And when I actually talk about in generalized states, how field theory arises in this thing.
Right. So could you have predicted the answer for this boundary contribution directly from physics without?
Well, not in this case. In some of the cases where the field theory gives you the answer, I'll do the field theory calculation. Because often it will be completely a field theory limit here. For example, in the one loop case, I'll show you an example where this boundary of the moduli space just becomes a thin tube. That becomes a field theory answer. So that is just given by supergravity. One does not need any string theory from it.
But here, even here, it's like a torus string theory with torus string theory, and then just some graviton propagation.
Yeah, exactly. But getting the final answer, that will be difficult because one has to do the integrals also. So we have to do integrals. So we have to take care of integrants like this. And you see, these are the boundary contributions. For example, when I'm looking at the separating node, this is the kind of the boundary contribution. At the non-separating node, when tau 2 goes to infinity, this is the boundary contribution. And these are kind of complicated. All I want to flash in this transparency is that this curly D's are all kinds of derivatives. This is the del tau 1, del tau 2, and del tau. So one has to take everything in. But again, at the boundary, things get simple. For example, at the non-separating node, this one, there is no contribution simply because there are too many 1 by imaginary tau 2's in the denominator. So this is cancelled. There is no contribution. However, at the separating node, there is a contribution. There's a 1 by tau here. Essentially, it comes from this derivative of phi. Remember, phi actually has a log tau. So log tau and derivative gives you 1 by tau here. And in the separating node, you have to do a contour integral around d tau. Around tau equal to 0. This gives you a non-zero answer. So there's a non-vanishing answer from the separating node. So that e to the 6 r to the 4th term in 9 dimensions. We'll see the other contributions in lower dimensions. But anyway, so first we'll see the 9-dimensional case. And lattice factors splits nicely into two lattice factors.
So this term, sorry, please go ahead.
No.
So the tau 1 and tau 2 were the diagonals in this thing which correspond to the complex structure of each of these guys. And tau was the off-diagonal which corresponds to the image.
And what you see is just exactly like partition function of the two products. And the fact that you don't see partition function times 1 point function, meaning you would have expected that there's an amplitude for producing a graviton.
Yeah. But that's essentially taken care of this. Taken care of this d tau by tau.
Yeah, that's because gravity topples so universally.
Yeah.
That you get. Yeah.
And this 1/4 tau is a propagator, is it?
No, this comes from derivative. See, del tau phi actually has a ordinate del tau of phi. So phi in the non-degenerating limit from the separating node actually has a log tau. So that gives you 1 by tau. That's the only reason that this contributes.
But Gautam's asking if you give a physical interpretation of it, isn't that somehow the length of this tube?
Yeah.
Because of the graviton.
Yeah.
So your modular transform tau goes to minus 1 by tau.
Yeah.
This is going to infinity.
So some e to the power minus p square tau integral of that.
But tau is a modular transform because you need that to be infinite. So psi 2 becomes just this. This is really the answer you get. And now these are actually what? These are actually the one loop, the genus 1 up to the 4, which is already calculated. So this is what you do the integral because in 9 dimensions you've already done this calculation before. And then you get this differential equation for the d to the 6 up to the 4. Then you just solve it. You get two contributions, from the homogeneous part which both have to vanish because the inconsistent structure is still correlation theory. So this is the leading model answer.
You get a very simple differential equation.
Yeah, exactly. Because it's BPS. And this proves some advantages in the literature because these are only calculated beyond 10 dimensions. So now let's look at genus 3 amplitude. There's only one to talk about the d to the 6 amplitude for term. And this is the expression here. This is a simple lattice sum. And again, you have the measure, the SP6 which is in very moduli space. This is roughly the same as what we have. The size of the period matrix changes. And again, you make use of this relation. And you get this equation here. And the overall normalization fixes in the 10-dimensional decompactation. So things work out much simpler than actually doing the integrals. So now we shall look at the next simplest case, the 8-dimensional case, the things happen.
And why did you have a total derivative term in genus 3?
Again, that vanishes because the integral was just 1. But this will come to So far, this was the warm-up example. The 9-dimensional case is the simplest one.
And it's simple because it's a differential equation with respect to just one parameter.
So that's why I decided to
What is differential?
Exactly. What is it? Because it's one parameter.
Yeah.
So now I want to look at the equations in lower dimensions. The things are more complicated. But at least the logic will be same. That's why I wanted to spend most of the time on this number. So let's go to 8 dimensions. But I think I want to retract to. Now the T duality group is SL to Z T and SL to Z U, where T and U are the scalar and complex structure moduli of the T2. T, the imaginary part is the volume, and this is B1 is the NSNS sector coming from the 2 forming 10 dimensions. There is only one of them, the B1, 2. And B2 is the volume of the T in the string frame. Now, perturbative equality of 2A and 2B implies invariance and interchange of T and U, while keeping e to the minus 2 phi T2 free. This is the 8-dimensional T duality invariant Dirac law. Perturbative equality implies interchange of T and U between the complex structure.
What is T2? What is T sub 2?
T sub 2 is V2, is the imaginary part of T.
So, sorry, the T duality group is this times. I mean, the first part is the T duality group, and the second part is.
No, the whole part. This is really O. This is O to 2Z.
Right.
O to 2Z, right? So it is invariance and the for this, at least for the amplitude ample. So I shall write down the expression for a general dimensional case, compactification TT for small d. Then I shall look at this in this case, because for this case, because then I don't have to repeat for other dimensions. We can write down the expressions here. This is the lattice factor here, this define it. Everything else is like what we had before. So now you already know what the definitions are. The lattice factor at genus G for TD compactification is given by this object. This is the volume of the d-dimensional torus in the string frames. This is the lattice sample. So small I and j go from 1 to d, the number of the metric and the directions of the metric and d that can be taken. And capital I and j in the direction of the period metrics will go from 1 to the genus. This is the proof of it. And of course, I am looking at the 8-dimensional case, so here the metric is given by this. This is determinant of G is really T2 square. So good determinant G is V2. And now again we use this relation. So the lattice factor T plus U gives just this. So this is precisely what you need because you want things to be very integral. So let's now begin. For the R to the 4 interaction we have this. Now this was actually the boundary term we had, which we had thrown away.
I couldn't see that differential equation.
Yes, which is what you had. So grad T plus grad U.
T is what is the.
T is the Laplacian on SL2Z T. This is the Laplacian on SL2Z U. So this is the moduli space Laplacian, the system moduli space Laplacian. This is the moduli space on the world sheet, the genus 2 world sheet. Sorry, in this case, the genus 1 world sheet.
I see.
This is the analog for the
analog of that. I see.
But now it's a manifest T duality invariant.
I see.
So that is the whole point. So now for the D4R4 interaction, sorry, for the R to the 4 interaction, this is what you get. This was the boundary term. So now I shall perform honest analysis of the boundary term to see where it goes. In fact, I'm doing it here because this is non-vanishing on the name.
In this 8-dimensional case, this differential equation almost looks like there is a symmetry between the T2 of the target space and the T2 of the world sheet.
Actually, that's what happens, isn't it?
Because I mean, it's like some kind of combined Casimir equals U.
In fact, if you write down the lattice, this lattice sum here, it can be written in the form. It is some minus pi square, G alpha beta. G I A alpha I. It can be written in this following, but this is the one sheet. This is the placement.
Yes.
This happens only in 8 dimensions. And here, alpha beta really what are the small i's here, capital i's are the torus. One is the one sheet torus, another is the placement. So this is the interaction here, and this is again. Now I want to look at the boundary terms carefully. This localizes the boundary of this moduli space, which is at omega 2 equal to infinity. So this is the boundary term. So we only this is something trivial integral. We have to just look at the finite contribution when omega 2 goes to infinity. And now the lattice expression I had given you earlier is not particularly convenient for this. Essentially, because in the exponential upstairs you have this 1 by tau 2, 1 by omega 2. So large omega 2 can be a little bit dicey. So what one has to do is do some Poisson distribution. So let us use an alternate representation of the lattice sum, which actually makes this divergence structure much more manifest. And this is how it is given. So now here there are no inverses of the period matrix elements anywhere. Everything is an exponential with no inverses. In fact, in string theory, this is actually the way you get it. Because now actually this is really between momentum and binding. the expression I had earlier was only momentum. So all the winding modes at points are the same. Okay, so here is momentum and winding is much more democratic in this. But now you see, this representation has the advantage of making the boundary behavior relevant expression simple. Because for example, you see when in this degeneration limits, these lattice sums here, they are exponentially vanishing. So in lattice contribution, this is non-vanishing only when all the integers are 0. So the leading order, the only contribution is this part for the boundary term. And from here, you immediately see, without doing any calculation, that this one, the term here, which will be only linear in omega 2 will contribute. Because you need a constant here. And linear in omega 2 here means d must be 1. Sorry, d must be 2. So such a term can be non-vanishing only in 8 dimensions. The prediction of string theory. And the right hand side is very simple, it's 4 pi. Because this is 4 pi into 1. And so this is then the equation, and the solution is just this. There's only one unique modular form of weight 0, which actually solves this. And again, coming back to the physics here, this is the log is a logarithmic, the infrared divergence in string theory. And this, I'll just comment on this, that this coefficient also could be fixed exactly done by doing a one loop gravity analysis in the field theory limit without taking string. This 4 pi could be fixed. So often in very complicated cases, I just fix this part of the amplitude, which is non-string directly using a field theory.
So you probably send this forward. T and U were defined how it is.
T and U were okay, so we have this T2 compactification. U was the complex structure modulus, and T was defined as T was volume.
Yeah.
So again, you immediately see that this trivially follows because it's a boundary term. On the other hand, when people actually originally did this calculation, one actually directly solves for the integrand. This is much more complicated. You have to know the entire term here, because here this to be regular force. It will be simpler, and you also show that this right hand side can be non-vanishing only in 8 dimensions. And it's well known because if we just for dimensional analysis, you see the r to the 4th term in 8 dimensions, because it's integral d8 r to the 4th, and r to the 4th is 8 dimensions, has 8 derivatives. This kind of log divergence. And that ultraviolet divergence shows up in strings as the infrared divergence. So this is precisely this thing is shown. In other words, this coefficient could have been calculated directly using field. It's good to see showing up strings. This is a calculation in maximal superunit, which people have done.
No, that's the finite calculation.
That's a logarithmically divergent.
Logarithmically divergent. But where is the divergence?
There's no divergence.
No, but you were.
There's an infrared divergence.
Match this.
There's an infrared divergence of this kind, log. Log is infrared.
So you were identifying this. What's the cutoff here?
Yeah. So what happens is the following. In field theory, what you get is a term of this kind, which is log some log lambda s r to the 4. In string theory, this becomes some minus alpha by mu, some scale. And this is an infrared divergence. In fact, what turns out to be the number, that number turns out to be here. Yeah, this scale actually turns out to be some 4 pi by 3 log of the log. Because after taking the log, it just becomes the kiloton. So this number 4 pi by 3 would have been calculated directly using field theory. And this precisely gives you this field theory, this 4 pi on the right hand side of the equation.
What's the relationship between the S there and the T2 there?
The S, this is an understood variable.
Yes, and that was just some parameter of the compactification.
No, this has nothing to do with this. When you actually, this was in the string frame, when you move to the Einstein frame, this equation is the local and non-local term in the effective equation. The log S r to the 4 is the non-local term of the effective equation, which is not the same. Okay. The other part, after converting to the Einstein frame, is a contribution to the local.
Oh, I see.
And that is the only part, the log part.
That gives you the
it's only that part which matters in this. So in other words, if you could have calculated this ultraviolet divergence logarithmic term in supergravity, you would have fixed this coefficient. And then people have done so. But I'm doing this because a lot of these cases, this amplitude directly takes from string theory, from field theory directly. Because they don't belong to string theory. So now let's look at the t to the 4 after the 4 term. Here it turns out there is no boundary contribution. I'll just give you details. This is the final answer. The product of two Eisenstein series. And Again, for d to the 6, there is again the boundary contribution, and this is what you get, the product of E3 times E3 and P1 plus E. This is really the proportional to the R to the 4 amplitude, and this is the new one. This also matches the resolution.
Okay, where from what you're doing here do you see that these amplitudes are simple because they're supersymmetric? I mean, the method you're using doesn't seem to rely on supersymmetry.
Exactly, I'll come on to that exactly. But the integrand which I'm talking about are very simple to supersymmetry. So, and the other cases could be, so let me for example give you the example of the heterotic string. So, I mean, here the genus 2, for example, the measure becomes very simple. Heterotic string is the bosonic measure times the superscriptive measure. The bosonic measure, for example, involves this height and inner denominator. We use a cusp form. But this height and difference completely cancels in a type 2 case because the left and right moves, everything cancels.
Ego-Cusp form is considered a complicated.
Well, that is also the leading one. So when you make a momentum expansion, you get things worse than that.
I asked because every time Atish gave a talk here, he would start the talk by saying, let's start with a simple example.
That is the zero momentum expansion. So that one
okay. No, it's very complicated for me.
Anyway, so up to d to the 6, r to the 4, this is what we get here. So this was supposed to look for genus 1. So now let's look at genus 2. Let me write down the expressions again. Again, these things are more or less already defined, so there's nothing really defined here. Again, integral is 1 here and the covers will be done. Again, the genus 2 we use this expression. Again, with a differential equation, we plus the transparency. So d4 r4 that turns out to be just the boundary 2. That's the answer in this.
Sorry, what was the notation gamma 2 to 2 again?
Gamma 2 to 2, yeah. Then let me give you the expression for gamma. Let me put here. Let me quickly go back. This expression. So even better, this is the more useful. So the last one is the genus, and DD is the proportion. So the genus 2 two-dimensional compactification is gamma 2 to gamma. Right, so this is the expression. And d to the 4 r to the d to the 4 r to the 4 is no surprise, and this is what you get. Now let's look at d to the 6 r to the 4. This is quickly to the answer because we have already done the analogous calculation in 9 dimensions. This comes from the separating node, and this is the 2 product of the r to the 4. But now I've left a dot because this turns out this is the first step that the non-separating node also contributes. Okay. But this I'm giving as a dot because I'll wait for the general case, so then I shall replace the answer in d equals integration. Non-separating. So now let me look at the genus 3 amplitude here. The answer. This is the genus 3 expression here, and again this boundary contribution vanishes, and you get this answer. Nice answer that this is not some of those resistance. So now let me let me look at the general dimension because the issue was in which dimension and how exactly these boundary terms contribute. Apart from that, more or less we have figured out. And we'll be using the relation. First, let me look at genus 1. This is compactification on TD and genus 1. This is the relation. For the R to the 4 amplitude, I already told you there's a 4, 5 in 8 dimensions. I'm not going to repeat it's the same. I've already done that. And the important thing is now you immediately get these expressions here. So these expressions now they come out very easily just from the properties of this derivative operator. And the fact that the integrants, each of them have very simple properties. But this is actually quite difficult because they are conjectured based on new duality. What will be the eigenvalue in arbitrary dimensions? And you see in 8 dimensions there's a log term here. This coefficient vanishes. So that actually that says we will scale it by an arbitrary function. We wouldn't have mattered. And the scale at this number not vanishing but equals 2. The scale would have mattered in the numbers.
Sorry, what did you say about duality here?
Because people originally guessed these equations
using you.
Using you.
But you've not assumed that you sort of in some sense prove you.
Yeah, exactly. That proves a whole bunch of conjectures because it's d into d minus 2 by 2 was a conjecture based on U2. You will calculate in various dimensions and you look at the answers d into d minus 2. It follows easily. And this part is the easy part. The difficult part is remaining this part. The r to the 4. For d to the 4, r to the 4 again we get this. And this is being conjecture immediately. It immediately comes out here. It's trivial how it is. And now this is the boundary term. Now you want to ask in what dimension this boundary term is converged. And this is the boundary term is E2 derivative of lattice minus lattice derivative of E2. And I have to keep the finite part as omega 2 goes to infinity. So this is basically if this torus here, and when omega 2 goes to infinity, we will the field is infinity. So for that, what I'm going to do is just use the expression for omega 2, for E2 here, and then it's trivial. I mean, I know the expression for E2, I know the del omega 2 behavior, and it's non-vanishing only in 6 dimensions, T4 compactification. And the coefficient is 12 zeta 3. This precisely agrees with the conjectures based on U2. And this can be non-vanishing only in 4 dimensions, in 6 dimensions. And I can note this eigen will be vanishing in 6 dimensions. So it's insensitive to the scale of the number. For 3 to the 6, again we get this. And again I use the expression E3 is again non-vanishing only in 4 dimensions. So back to a 6 dimensional torus. We have precisely 25 zeta 5 by pi, which follows from is also the conjectures based on duality. And again this coefficient vanishes in precisely 6 dimensions. So again this is insensitive to the scale. This is genuinely supergravity fields. I mean, some of these calculations have really not been done in supergravity, but in principle they can be done. But I think particularly this one has not been done. Okay, so first so good for genus 1. Now let's look at genus 2, which is much more complicated. And so now the D4 R4 amplitude satisfies this equation. This is 1 into Laplace activity lattice. Now the question in which dimension does this give a contribution? The contribution of this separating node always vanishes because it's 1 here. The separating node was the integral contour integral d tau, and there's really no 1 by tau to control in the middle. So let's not talk about that. That we know vanishes. So now let's look at the contribution from the non-separating node. This actually involves the boundary term going from the T2 derivative, because the non-separating node was the node where T2, imagining part of T2 was going to be infinite. And I'll give you the answer. I mean, here one has to carefully look at how this curly T2 has, what contribution it does. And the important thing to note in this limit, the lattice factor simplifies. Okay. The lattice factor actually has the lattice of this remaining one-dimensional this T2 times this factor here. And this del T2 term actually has two kinds of contributions. One from ordinary derivative of T2, another from ordinary derivative of T1. Let me first give you the answer, and you can work it out in the del T2 term actually contributes this kind of term. And we have to keep the finite part as imagining T2 goes to infinity. And the T2 dependence is very simple. It's over here, the derivative, and over here. So D must be 2. Excuse me, D must be 4. And then you do this integral, and it's non-vanishing only for D equals 4. So this part is gone. You have to do the integral over tau. Right? And tau you can actually work it out when you work out the constraints only based on the fundamental domain of SP4Z. Tau actually turns out to be very nice. Tau is a very physical simple interpretation. So take a torus with, so this you have to do this integral over tau and tau 1. Okay, so what is integral over tau? Tau turns out to be the coordinate on the one sheet of a torus with complex structure tau 1. So that integral can be done very easy, just based on what you know what it is. And this is what you get. And what you are left with is the R to the 4 interaction at 1. And this precisely proves some conjecture based on the So of course, this was this limit. Let me just draw the diagram. This was this limit where we have this kind of a node here of the non-separated limits. But what about the limit where this one also shrinks? So first I go to the boundary of the tau 2 moduli space. Then I go to the boundary of the tau 1 moduli space. And that is precisely the field theory. Because then you have imaginary tau 2 going to infinity, imaginary tau 1 going to infinity. These become the two Schwinger parameters of the field theory. But the ratio imaginary tau 1 imaginary tau 2 will be finite. So this is the field theory. And so this is the field theory limit, which I have written here. And one can do the integral. Then one does not demand that the imaginary tau 2 divergence cancels. We just localize whatever is left in the integral to the boundary of tau 1. And then see what happens. And this is what you get. So this is constant order 1 and non-vanishing only when d is equal to 3. So in 7 dimensions. Because d minus 2 must d by 2 must be equal to 3 minus d by 2. This is precisely the case where field theory divergence is shown. But it's easily, this dimension easily follows from string theory. These are almost 0.
Why does it follow that if you interpret this in terms of the field theory diagram, then the two Schwinger parameters have to be, their ratios must be finite?
Because the field theory diagram is just this.
Yeah.
These are the various Schwinger parameters. These are infinite things. So the ratio should be finite. This is field theory. I mean, there is no choosing between this loop and this loop.
At a generic point in the integration space, the ratio is finite.
So I have fixed everything except this C here. The coefficient was the field theory coefficient which I did not fix. But that can be fixed in a supergravity. This will just give you the result. It's a long calculation one can do in supergravity. So that fixes it. And this was the stringy part, this is the supergravity. So this gives it complete D4 R4 interaction. So now let's look at the D6 R4 interaction, the last of the genus 2 interactions. So this part I already told you before. This comes from the separating group, where it factors into product of two genus combinations. Plus this dot, which I left even as a dots for the 8-dimensional interaction. What are the contributions from the non-separating? And again, you see there must be some field theory contributions. So we could tell you how they are. So this is really a complicated answer, but all you want to remember is this is localized at imaginary tau 2 into infinity because it's a non-separating node, and there's a phi, roughly there's a phi derivative of lattice minus lattice derivative of phi. Again, one has to look at del tau 1 derivative and del tau 2 derivative. And del tau 1 derivative is this kind of derivative when you localize field theory. They take the ratio of divergences. And this precisely is a finite contribution only in 8 dimensions. And this was the term which I left as dot to say 8 dimensions. That will finish the contribution. And so the 8 dimension actually, this was the term which I left as dot. And the coefficient now fixed using supergravity.
This is just a constant.
Just a constant. Because it cannot be moduli dependent because it's supergravity. Okay. And so this is this answer, which is the following. This is sum of eigenstances, product of eigenstances in a constant. This guy satisfies this point. This again has been conjectured, this structure based on duality. Okay. So now let's look at, this was the del tau 1 contribution, now let's look at the del tau 2 contribution. There is a bit of mess, so let's go to that systematically. So, I mean, basically I had this Zahn powers with Belling, and I want to expand that for large imaginary tau. I want to look at asymptotes. So that the leading term, which has several transparencies, the details don't matter, but the leading term was linear in imaginary term. This contribution actually vanishes because there are two terms with exactly the same contribution. And the order 1 contribution also turns out to vanish because it does not give anything moduli in bed, so it must cancel the whole amplitude. And there was you go much south, you take the imaginary term, this vanishes, order 1 vanishes, then the 1 by imaginary tau 2 term. That turns out to be a non-vanishing answer. Let's see what it is, and that vanishes by non-vanishing only in 4 dimensions. And you have this integral over the expansion of the powers of the Riemann around this limit. And let me recall for you that this phi 1 was given by this. And this one, as I told you, is the integral over the coordinate or torus of modulus tau. Now this d2 to actually integral vanishes. It's trivial to see. And all that matters is E2 is left here. And so what you're left with is an integral here, d2 tau E2. And this is going on because there's no tau 2, this is no tau dependency. So finally, what you are left with is just this modular integral. And if you remember, the d to the 4 up to the 4 term precisely had E2 and the integral. So it actually proves that when you fix the coefficient here, it's only to 20 by pi square. 4 dimensions, this non-vanishing only in 4 dimensions this time. So again, it's consistent with duality discontinuity. So finally, let me do the last part. Is yet you go down lower in the order. This is the 1 by imaginary tau 2 square contribution, which actually again gives a field theory contribution. And to complete the list, and the coefficient can be fixed using Perturbative supergravity. This is the complete answer for the genus 2 d to the 6 contribution. Which is all the Perturbative divergences. So now let us look at the genus 2. I just quickly give the answer because it is more complicated, but I think the logic is roughly the same. So again, you have to localize on the boundary of moduli space. So for genus 3, I mean, there will be this. There will be one of these nodes in the non-separating node. It will come from here. This is where we are generating string interaction. This will involve a genus 2 contribution. Then you kind of remove this man a non-separating node. Then you get another stringy contribution where we have genus 1 amplitude there. And the other, all of them go to infinite, but the ratios are finite in certain ways. That gives the field theory. So that coefficient is field theory. So this part is very easy, I did the calculation. And the remaining two numbers are just fixed using field theory. Some of these calculations have been done in field theory, others have been conjectured based on duality. The supergravity calculations can be done with duality.
But you said only one of it can be calculated using field theory.
Right. So the point is, say no, this one is a generally stringy one. But when you actually have this one also going to infinity, the ratio of that can be finite. So that part gives you a field theory. So that actually turns out to be in a field theory limit, that's a That's the non-trivial vertex counter term. But the vertex is string. The vertex is a R to the 4th term. But then the loop is a field theory. I mean, it's like when in field theory, when you actually have these 4 graviton amplitude like this, the vertex itself can be string. Here in this case, the vertex itself is the R to the 4 graviton amplitude. The rest is the field. So this vertex is put in by hand, this case. And then you put the field theory. And then all the 3 sugar parameters go to infinity, the ratios are fine. That is the genuine field theory, where there is no stringy vertex. So this, yeah, you're right. This one, because little bit of string theory was very weak. So this fixes these coefficients. So I'll just say that, I've done something with this BPS interaction, lot remains to be done, obviously. I mean, you name it. Non-implicit operators, less unknown supersymmetry, time limited diagrams, resolution of singularities, unknown diagrams, and of course, this also apparently is useful to mathematicians because these kind of modular equations are new to them. And the same thing.
No questions from ICTS? Okay, questions, comments?
I just want to know, you all say the 4 graviton amplitude continues only R4. But even for lower R, there can be 4 G terms in the action, right? Even R square, say, there can be gammas there.
But the R square term vanishes. The leading contribution, correction after R is R to the 4 in type 2 in maximum supersymmetry. In heterotic theory, for example, the leading contribution is R square.
Okay.
So that is the leading contribution to 2 graviton.
So you call whatever is 4 graviton and number of derivatives as R to the 4 d to the power that not.
This is the one which is the linearized level is 4 graviton. But the non-linear level is the 5, 6 infinite number of gravitons.
Starts at 4 gravitons.
It starts at 4.
So, your analysis was for various terms, various perturbative contributions. Now, at a particular derivative order, there are also non-perturbative contributions. In the cases that you studied, have those also been conjectured?
Yeah, I had already some conjectures for 8 and 9 dimensions. These turned out to be the perturbative ones. So then, being generalized to lower dimensions. So, take the utility invariant modular form, there are conjectures for that. That is for the R to the 4. There are conjectures. T to the 6, there are some recent conjectures, and T to the 4 also there are some conjectures. But then we expand around big coupling, this is what it means.
And these differential equations of these terms satisfy? I know very little about this, but I vaguely have the impression that the full term, including the dependence on the dilaton and so on, sometimes satisfies differential equations because of supersymmetry. Is that right?
Yes.
So are these differential equations in any way related to those?
Yes, you take that, for example, you take the Laplace operator, expand around this thing, so throw away all the derivatives coming from Riemann sector terms. This will actually be the full U-duality invariant Laplace this thing. We'll have the T-duality invariant but which I had, plus the derivative of the dilaton.
I see.
The derivative of dilaton just actually, in particular for the log term, this is the one which gives you the eigen.
I see. So can you derive your differential equations from the supersymmetry differential equations?
Well, if you can prove U-duality, this follows the concept.
I see. So you're saying that plus U-duality implies your eigen. So your work has a check of the U-duality.
Exactly. Proving some conjectures based on U-duality. Because if you take the U-duality invariant equation, that's expanded in perturbation theory, you will get this equation.
And suppose so you were talking only about type 2 theories, right? What about tetrotic theories?
Yes, it should be doable. Wherever you have a reasonably compact expression for the amplitudes, it should be doable. Like even for example, for the simple case like that, the 4 gluon amplitude in heterotic string theory in 10 dimensions, flat space 10 dimensions. Not much has been done, like the expansion of the lower range expansion has been done. Even this type 2 expansion is kind of feasible. Surprisingly, this has not been done at all. Because you know the expression, even the genus tree, you know the expression. Nothing has been done.
And just to ask again about the tie-up between this and supersymmetry. Now suppose you take one of these stable non-supersymmetric heterotic theories.
Right.
There you would expect the answers to be very complicated.
Perhaps, yeah.
Yes.
Yeah, perhaps, maybe some of the leading order terms, maybe in flat space 10 dimension or some simple cases might be trying to not beyond that. But the leading order ones are typically fixed by anomalies to not beyond one level stuff like that. But the ones which are genuinely interesting like D4 or D6, those might be too complex.
So this log S calculation that you described, I mean, so you do a field theory calculation. So let me ask it again. So of course you have the this renormalization scale going in there. So how does it not appear in the expression that you have?
If you directly look at it from here, there's a field theory. So actually at the end what happens is, right, so you have something in log minus, let's say, some log details don't matter basically.
Yeah.
So now what you go is from the
This is just a one loop calculation like this.
And then you go from the string frame to the Einstein frame.
Yes.
Right? To the this thing, to the local part of the interaction, you get a term like some constant versus and all these stuff. And this one, when you look at the differential equation here, the eigen will actually exactly vanish in this dimension. So log didn't matter. In fact, when you look at this calculation that people have done for after the 4 term in string theory, and I wrote down this answer, there was this P1 P2 already, which was this minus 5 log T2 T4. This was the calculation number I just recent Kopilowski and Jan many years ago. And I actually ignored a scale, it is actually a scale. Just set to 1. And the scale involves the volume asteroid constants and pi.
So that's just one.
This is a number. One very good. In fact, Violin and others did this calculation in a different way. They actually, so the integrand is just 1. So they just 1 by, Einstein series ES T2 bar, limit is tending to 0 minus, because E0 is just minus 1, relative minus 1. Then you do it for arbitrary S and take the limit S going to 1. Sorry, S going to 0. Now that is a different normal relation. There's a different choice of scales here, how you choose to normalize. Because at the end of the whole answer, the whole string answer is a sum of the local and the non-local terms. And how you choose to split the logs between the local and non-local is up to you.
Sorry, one more question. There have been these recent cases by Yin,
Yes.
trying to compute terms in the effective action, I believe in K3 compactification.
Right.
I just wanted to ask whether there's any.
Actually, that is for the leading term, they get a Laplace equation, and for the subleading term, they get a Poisson equation represented with the source term 0. So what happens is essentially, when you make an expansion of any action, you get something like S1, S0, S1, S2. This is a derivative expansion. The details don't matter. So this is with 2 derivatives, this is a higher derivative. This one typically satisfies the Laplace equation. This one will satisfy the Laplace. This one will satisfy Poisson equation with the square of this one is the source term. This is follows from the source term. So that is what they do.
So you're saying they get similar structure of equations.
Yeah. Their analysis is of course using this helicity, but the answer is exactly what.
And are they able to constrain also the return dependence? Is their analysis perturbative term by term or?
No, their analysis will be, if they're looking for effective action, will be non-perturbative.
Non-perturbative. I see. So, but if you could confirm their analysis, perhaps using your techniques, they also assume some U-duality kind of.
Yes.
They assume such a. I see. Would that be possible to do in practice?
I think that will be possible because they are the expressions for this various loop integrals are reasonably easy. I mean, because it's K3. I mean, if for example, you think about it, the K3 times T2 compactification R squared term is absolutely independent of the K3 moduli. So it's only this plus E1 T2. This was a Harvey and Moon T2. This is R squared term, and beyond that, all other high derivative terms involve only graviton and which is vanish. So it's easy. I mean, isn't this is an abstract?
Other questions?
Yeah, K3 is one case where things might be able to do because the conformal K3 is well understood.
Well understood. Okay, thanks.